So there's one more class of special square matrices, and these are called the symmetric matrices. So the definition, a square matrix is symmetric if it is equal to its transpose. So this means the transpose. So there's a video about the definition of a transpose of a matrix. And so let's just, so we can get a feel for what they look like. So the matrix, say, 7, 2, 2, 5. This is symmetric because if you take its transpose, well, when you take its transpose, you just swap the role of the columns and the rows. So it's equal to its own transpose, so that's good. Or something like 1, 3, 5, 3, 5 minus 4, 7, 8, 8. So if you watched how I wrote it, you can see, understand the symmetry. That's why they're called symmetric matrices, but this is also symmetric matrix. So it basically just means that if the first row is the same as the first column, the second row is the same as the second column, the third row is the same as the third column. So again, if you take the transpose, you're just swapping the role of the rows and columns. And it's actually equal to its own transpose. So any diagonal matrix is clearly symmetric because you just swap the rows and the columns and you preserve equality. So these are what symmetric matrices look like. So the reason they're called symmetric is because there's this symmetry about the diagonal. So you can do anything you want on the diagonal, but then you have this symmetry that's sort of like going across. So you have, here's the symmetry, here's the symmetry, here's the symmetry. Those entries have to be the same. So it's like symmetric across the main diagonal. That's why they're called symmetric. So let's talk about some properties. So here are some properties of symmetric matrices. So the first is that 1, if A is symmetric, then its transpose is also symmetric. And this is just tautologically true because symmetric means it's equal to its own transpose. So you need to show that the transpose of the transpose is equal to itself. But that is just one of the properties of the transpose. Yes, it is. Yes, it is. Is equal to itself. And since A is symmetric, we already know that it's equal to its own transpose. So this says that the transpose of the transpose is equal to itself. So, I mean, you can think about that, but it's not very profound. Second nice property is that if A and B are both symmetric, then A plus B and A minus B are also symmetric. You understand what I'm trying to write. And the third property is that if A is symmetric, and K is any number, then you can scale the matrix A. Ka is also symmetric. And so these properties just come from the properties of transpose. So these properties, they all the properties of the transpose. So you can watch the other video where I define the transpose and I list some of the properties, but all of these properties just follow from that. Okay, and here's a fourth property. If A is symmetric and invertible, then its inverse is also symmetric. And this is, again, these all follow from the properties of inverse. So the idea here is just very simple, that, again, the A inverse transpose, one of the properties of transpose is how it interacts with the inverse, and that's equal to A transpose inverse. But if A is invertible, if A is symmetric, then A is already equal to its own transpose. So, let me erase this. So, this says that so if you just look at the bookends here, this says that the transpose of this thing is equal to this thing. So, by definition, this says that A inverse is symmetric. So, really, none of these are that big of a deal. Now, there's something cool you can do. So there's a way you can get a symmetric matrix from any matrix. So there's this cool little construction you can do. We can, given any matrix, not necessarily symmetric, M, we can construct this new matrix by taking M and multiplying it by M transpose. So this is a new matrix, and this matrix is symmetric. So this is a cool little, say, proposition or just an observation. And it's clearly symmetric just because just by properties of the transpose, because M times MT to be symmetric means that it should equal its own transpose. When you take the transpose of a product of matrices is the transpose of the products in reverse order, and the transpose of the transpose is just the matrix itself. So again, this literally proves I'm taking the transpose of this whole thing, and it's equal to itself, and therefore that shows that this thing is symmetric. So that's where it comes from. It's just kind of a cool little thing that you can do. So as an example, so let's do an example of this. If we took the matrix, say 1, 2, 3, no, I don't want to do that. 1, 2, 1, minus 1, 3, 2. So this matrix is not symmetric, but if we multiply this by its transpose, then, well, you're basically doing the dot product, so you get 1, 4, 6, and then here you're doing -1, 6, plus 2, I don't know, -1 plus 6 is 5, plus 2 is 7, and then when you do that you get -1 plus 6 plus 2 is 7, and here you get -1. Now you're just doing the dot product, so that gives you 1 plus 9 is 10 plus 4 is 14. So this is clearly symmetric,